Hello everyone, this is Professor Mahesh Pardeshi from Parvatibai Genba Mose College of Engineering, Wagholi, Pune. Today we are discussing thermodynamic properties and the today's property is capillarity. Dynamic properties, we will today discuss the capillarity. See, first of all, you can understand by the definition of the capillarity. Here you can see capillarity is defined as the phenomenon of rise or fall of a liquid surface in a small tube relative to the adjacent general level of the liquid when the tube is held vertically in the liquid. It's just a rise or fall of a liquid surface. What is the meaning of capillarity? Capillarity is nothing but the rise or fall. It is the rise or fall of the liquid surface. See, here they are written as small tube. Small tube. Here you remember that the diameter of this tube should be less than 6 mm. Diameter of the tube should be less than 6 mm. Okay. Now here rise or fall. It is related to two liquids. For example, if we consider water, and if you insert this small tube into the water level inside the tube will get rise will get rise. This is in case of water. The other example we can take for mercury. In case of the mercury, if you insert that small tube into the the liquid level inside the tube gets fall down gets fall down. These are the two examples of the capillarity for the rise or fall of a liquid level. Okay, the examples are water and mercury. Okay, now see, the rise of liquid surface is known as capillarity rise. If the rise of liquid surface, it is known as capillary rise, while the fall of liquid surface is known as capillary diffraction. Capillary depression. Okay, the adhesion between the walls of a tube and the liquid molecules is strong enough to overcome the mutual attraction cohesion of the molecules and pull them up the wall. Hence the liquid is said to wet the solid surface. This concept you can study by using example. See, what is the meaning of cohesion? Cohesion is nothing but the attraction between the similar molecules. Cohesion is nothing but the attraction between the similar molecules. Means suppose we are considering the liquid as a water, then cohesion is nothing but the attraction between the water molecules. Okay, and what is meaning of this adhesion? Adhesion is nothing but the attraction between the different molecules. Here the different molecules are liquid molecule plus the wall. Okay, tube. Okay, so here the attraction between the tube and the molecule, liquid molecule, is called as adhesion. So in case of capillarity, what happens? This adhesion force is more than this cohesion force. Means this adhesion force is more than this cohesion force. What happens? The bond between these two molecules, similar molecules, is breakdown. The bond between the cohesion bond between the similar molecule is breakdown, and the bond between the tube and the liquid molecule is strong bond, that is adhesion is strong. So here in case of capillarity, adhesion is always greater than this cohesion. Adhesion is more than cohesion. That's why the movement occurs. If cohesion is less than this adhesion, in that case only the movement happens. Liquid may get up or liquid may get down. Means rise or fall of liquid depend on these two properties, cohesion and adhesion. Okay, Hence, the liquid is said to be wet the solid surface. In that case, if the adhesion is more than cohesion, in that case, the liquid is said to be wet the solid surface. Okay. It is expressed in terms of centimeter or mm of liquid. Its value depends upon the specific weight of the liquid and the diameter of the tube and the surface tension of the liquid. This we will discuss with a reference to the formula. At the end of this session, we will discuss the formula for this capillarity rise or fall, and you will get the knowledge of this all the terms in that formula. Okay. Now, see the diagram. Here you can see that this tube is inserted in the water or liquid, and due to the capillary action, this liquid get rise into that tube. Liquid get raised into that tube, and this is the height of capillarity rise, h. H is nothing but the height of capillary rise. Okay. Now see here the expression of capillary rise. Consider a glass tube of small diameter d opened at both the ends and is inserted in a liquid, say water. Means here we are using water. The liquid will rise in the tube above the level of the liquid. Here the water level in the tube is above the water level in the tube, water level in the liquid adjacent to that. Means here the level of the liquid is this, and the level of the liquid in the tube is this. Okay. Let h be the height of the liquid in the tube. Under a state of equilibrium, the weight of the liquid of the height h is balanced by the force at the surface of the liquid in the tube. Here, under the state of equilibrium, the weight of the liquid of height h is balanced by the force at the surface of the liquid in the tube. Okay. But the force at the surface of the liquid in the tube is due to the surface tension. Here the surface tension force is acting like this. Here you can see that surface tension force. Okay, this one. Now let let sigma be the surface tension of the liquid. Theta is the angle of the contact between the liquid and the glass tube. The weight of the liquid of the height h in the tube is given by area of the tube into height. It will gives you the volume. Area of the tube into height, it will gives you the volume into rho into g. Okay, this total will gives us the weight of the liquid of the height h in the tube. So we will get this expression: pi by 4 into d square is the area of the tube into h into rho into g. Okay, where rho is the density of the liquid, where rho is the density of the liquid. Next, the vertical component of the surface tensile force, the vertical component of the surface tension force, sigma into circumference into cos theta. Sigma into circumference into cos theta. Circumference is founded by the pi d. Sigma into pi d into cos of theta. Now, by comparing these two equations, here pi by 4 into d square into h into rho into g is equal to sigma into pi d into cos theta. So from here we will get the height h, capillary rise height h. Here we will get the expression for capillary rise as 4 sigma cos theta upon rho gt. 4 sigma cos theta upon rho g d, where theta, here you can see that this theta, I will show you. Theta is this angle. It is here denoted by phi, but actually this angle is theta. Okay, in case of water, in case of mercury, this angle is theta. Okay, now here you can see that uh, here the value of theta between the water and the clean glass tube is approximately equal to 0, and hence cos theta is equal to unity. Cos theta is equal to unity. Then rise of water is given by h is equal to 4 sigma upon rho gd. Here the cos theta is equal to 1. Here the cos theta is equal to 1 in case of water. In case of water, H is equal to 4 sigma upon rho GD. This is the final expression for the capillary rise in case of water and the glass tube. Okay. Now the contact angle between both the liquids and the solids. If theta is less than 90 degree, the liquid is said to be wet, the solid. However, if theta is greater than 90 degree, the liquid is repelled by the solid and tries not to wet it. This is happen in case of, I will just give one example for that. Wet the solid and does not wet the solid. In case of the water and the glass tube, in case of water and the glass tube, you all of might seen that the water wets the solid surface, that is the water wets the glass tube. But see, in case of the plastic sheet and the water, if I drop one water droplet into the plastic sheet, what happens? That water does not wet that plastic sheet. Okay. Here in the second case, the theta is greater than 90 degree. Theta is greater than 90 degree. What is the example? Plastic sheet and water droplet. Okay, understand? And in this case the example is water and glass tube. For example, water wets the glass but not the wax. Not the wax. Mercury on the other hand does not wet the glass. Mercury also does not wet the glass. Okay. Now this is the examples. Next part is expression for the capillary fall. Expression for the capillary fall. Here the diagram is given as wetting fluid and non-wetting fluid. Wetting fluid and non-wetting fluid. The container is glass tube. Here both the containers are the glass tube. First container contains the water. First container contains the water. So here water is stored in the glass tube, so that the water get wets this glass tube. That's why this is the wetting fluid. That's why this is the wetting fluid. But in second case, what happens? Mercury is stored in the glass tube. Mercury is stored in the glass tube. This mercury does not wet that surface of the glass tube. That's why this mercury is called as non-wetting fluid. Mercury is called as non-wetting fluid. Okay. And the difference between rise and fall, here in the it is given in second diagram. You can see that in case of the water, as the water is a wetting fluid, and here the adhesion force is more than the cohesive force, here you can see that the water level rises at the surface of the glass tube also. Here you can see that. Okay, adhesion force is more than cohesion force. And here you can see that rise of liquid level in the glass tube, that is capillary rise. That is capillary rise. And in the second case, in case of the mercury is the non-wetting fluid. Mercury is the non-wetting fluid. In case of the mercury, the cohesive force is more than adhesive force. Here the cohesive force is more than adhesive force. Here you can see that due to that highest cohesive force, the diagram or the mercury does not attracted towards the glass tube. Here you can see that the shape of the liquid is like this one. Okay. And here of course there is a fall in the liquid level in case of mercury. Fall in the liquid level in case of mercury, because cohesive forces are more than adhesive forces. Cohesive forces are more than adhesive forces. Now see expression for the capillary fall. If the glass tube is deep in the mercury, the level of the mercury in the tube will be lower than the general level outside the liquid as shown above. Here you can see that the level of the mercury is lower than the general level outside the tube. Okay. Now here h is the height of the depression in the tube. This one here, height of the depression. Okay, this is filled with the mercury, all this part. Then in equilibrium, the two forces are acting on the mercury inside the tube. First one is due to the surface tension acting in the downward direction, and it is equal to sigma into pi d into cos theta. We already discussed this part. Surface tension force is equal to sigma into circumference into cos theta. Therefore sigma into pi d into cos theta. Okay, this sigma is the circumferential force, this one sigma acting on this direction and this direction. Okay, second force is due to the hydrostatic force acting upward and is equal to the intensity of pressure at a depth h into area. Intensity of pressure into area. Okay sir, this one is the hydrostatic force, this one is the hydrostatic force. Now here we can compare these two forces. We will get this one is the hydrostatic force. By comparing these two, we will get sigma into pi d into cos theta is equal to rho gh into pi by 4 into d square, into pi by 4 into d square. So expression for capillary fall, the final expression will be h is equal to 4 sigma cos theta divided by rho g d. 4 sigma cos theta divided by rho g d. In the last case, in case of capillary rise, we are using water. In that case, this term cos theta is unity, that is 1. This cos theta is cos 0 is equal to 1. That's why the final equation becomes 4 sigma upon rho g d. But here we are dealing with the capillary fall. Here we are dealing with the capillary fall. That's why the final equation becomes h is equal to 4 sigma cos theta upon rho g d. And here the value of theta, here you can see that value of theta for the mercury and the glass tube is 128 degree. Is not 0, it is 128 degree in case of mercury and glass. In case of mercury and glass, the angle theta is 128 degree. Okay, this is all about the expressions for the capillary rise and capillary fall. Okay, thank you for this today's session. Thank you.